Okay, here we're going to be continuing our discussion on neurons. So if you remember, we finished with a number 3 all or nothing principle for yesterday's, or not yesterday's notes, but lesson 2B notes. So this is starting with 4, and we're starting with neurotransmitters. So neurotransmitters are chemical messengers that allow neurons to communicate to one another. Okay, neurotransmitters are chemical messengers that allow neurons to communicate to one another. Okay, so on the next slide, so we're going to write a small a with, or lowercase a with types of neurotransmitters. And by the way, the NT is something that you should use from now on for neurotransmitters instead of writing the whole word out. So what I want you to do here is I want you to pause me and copy this chart down in your notebook. And I would give each row like 4 lines in your notes to make sure that you have enough room. So pause me and copy this down as we talk about neurotransmitters. Okay, so these are 6 neurotransmitters that we're going to be responsible for. There are other neurotransmitters that neurons use to communicate. And it's a fine line between getting, a lot of information, getting too much information, too little information. We're on just at the beginning of understanding what neurotransmitters are. And it's way too simplistic to say that a neurotransmitter is only responsible for this, because it's a chemical mixture of other neurotransmitters, as well as the one that we're talking about, the amount of this, as well as others. So we're taking a fairly simplified view of it. So just kind of keep that in mind as we talk about it. So the 6 we're going to talk about are acetylcholine, or ACH, dopamine, norepinephrine, serotonin, or GABA, and glutamate. So let's start with ACH, or acetylcholine. ACH is responsible, and this is what you'll write, in the description square. It's responsible for movement, attention, learning, and memory. Okay. So acetylcholine has a number of responsibilities. Too much acetylcholine in the brain is not something that we have to worry about, but too little is. If a person has too little ACH, what tends to happen is we're beginning to see the onset of Alzheimer's disease. So too little ACH in the brain is associated with Alzheimer's. Okay. Dopamine is another neurotransmitter that has a lot of responsibilities, but the one that we're going to be most concerned with is it's the reward center in the brain. Okay. So when you accomplish something and you feel good about that accomplishment, that high that you get after getting a really good grade in a test, or winning a game, or, anything that is important to you, any sort of success, is because your brain releases dopamine, and that release of dopamine makes you feel good. Okay. You can have too much dopamine in your brain, and too much dopamine is associated with schizophrenia. Okay. We'll talk more about that when we talk about schizophrenia, but it's an important thing to also understand for this chapter. Too little dopamine is associated with Parkinson's disease. Okay. So if you're not aware of Parkinson's disease is a disease that involves tremors. So as it progresses, the tremors become worse. And as of now, Parkinson's is a disease that does progress, does get worse, because once the dopamine starts to decrease in the brain, the decrease continues. And obviously the effects will happen. Maybe also in the description, write the word addiction, because dopamine is a chemical that is associated with addiction, which makes sense because it's the reward center. So a lot of drugs play on dopamine, and we'll talk about how that works in this video too. But cocaine, for example, mimics dopamine and makes a person feel good. And so what happens in turn is then the brain will reduce its own levels. And again, we'll talk more about that later in this video. Norepinephrine is responsible for alertness and arousal. Okay. And too little, we're going to skip the too much again. Too little norepinephrine is something that can affect our mood and is linked with depression. Okay. Serotonin is important for a number of things. It's also a mood neurotransmitter. So mood, sleep, hunger, and arousal are all things that serotonin will be involved with. Too little serotonin is also related to depression, also OCD, as well as eating disorders. Okay. You're not going to probably see a question that says, so-and-so suffers from depression. Which neurotransmitter are they lacking? You're not going to see norepinephrine, dopamine, serotonin together. But serotonin tends to get the most credit for being related to depression. Okay. Then we have GABA. GABA is a neurotransmitter that it's called an inhibitory neurotransmitter, which means that it blocks communication in the neurons. So we have excitatory neurotransmitters or neurons, which cause us to get excited about things. And then we have inhibitory ones that are important too, because we don't want all our neurons firing at once. That would be problematic. So we have inhibitory neurons that are basically saying, don't fire right now. So GABA is an inhibitory neuron that's related to anxiety. All right. And as you can probably guess, too little GABA will tend to result in anxiety. That's probably the biggest one, the most important one, but it also is associated with seizures and insomnia. Okay, and then our last one is glutamate. Glutamate is associated with learning and memory. It's also one of the biggest excitatory neurotransmitters. So glutamate's the biggest excitatory one. GABA is the biggest inhibitory one. Too much glutamate, like too much dopamine, is linked with schizophrenia, and too little is associated with seizures and migraines. So let's go through and circle some words just to make sure that, because there's some things that we're doubling up on some words here. Like we'll work from the bottom up. So for glutamate, circle the word seizures. GABA, circle the word anxiety. Serotonin. Of those three, let's go with depression. Okay, let's skip the norepinephrine circle right now. In fact, no, let's go to the description and circle the word arousal. For dopamine, it's really all three of them. Let's circle reward center, Parkinson's, and schizophrenia. For acetylcholine, Alzheimer's we'll circle, as well as let's go with movement and memory. Okay, just to kind of delineate, because we do have some things that we're doubling up on. Okay, so let me go here for me. Okay, so let's talk about how this works. So we're looking back at our neuron, right? And this is what we call the presynaptic cell. And what we mean by that is this is the sending neuron, and this is the postsynaptic cell. And what we mean by that is this is the receiving neuron. So you remember from our neuron discussion that this is a synaptic vesicle, this little bubble, and inside are neurotransmitters. And as the charge comes down the axon and hits, a synaptic vesicle, it releases neurotransmitters. Now here would be the dendrite of the receiving cell, and they have what we call receptor sites. And these receptor sites accept the neurotransmitter or certain neurotransmitters that come across the synapse. So if serotonin gets released, for example, and this receptor site receives serotonin, it's going to get attached to this. And if enough serotonin hits this dendrite, then this neuron will fire as well. If it's, if that's what is concerned with right now is serotonin. So there are two problems that can happen. This neuron might not release enough of the neurotransmitter to get across. It might release too much to get across, or the receiving neuron might have too little or too many receptor sites for a particular neurotransmitter. So if this receiving neuron only has one receptor site for serotonin, for example, and this neuron releases, for example, 5 neurotransmitters of serotonin, again, I'm simplifying it, but if it releases 5 neurotransmitters into the synapse, but this receiving neuron only has one receptor site, then this receiving neuron isn't going to get enough serotonin, which could result in, again, depression and things like that. So this is when we look at a chemical viewpoint of our behavior, right? We talked about how do we explain behavior in a given context, and neurotransmitters are one of the ways that we do that, okay? Let's talk about some outside factors related to neurotransmitters that we need to understand. So an agonist is something that is excitatory and mimics a neurotransmitter. Okay, an agonist is excitatory and it mimics a neurotransmitter. So if I go back here, an agonist is something from the outside that sneaks in and fills in a receptor site. So a really good example is like cocaine and dopamine, right? So if the brain releases a certain amount of dopamine to make you feel good, but it doesn't release too much, what happens is the cocaine will slip in, fill the receptor site for dopamine, and then this nerve cell will be excitatory by the agonist, the dopamine, and not by an actual neurotransmitter. Okay, so an agonist, when we underline the word mimics or highlight or circle the word mimics, because it is copying a neurotransmitter. Okay, an antagonist is the kind of the opposite of an agonist. Okay, an antagonist gets in and blocks neurotransmitters from getting across the synapse. Okay, an antagonist gets in and blocks neurotransmitters from getting across the synapse. So if we go back again, an antagonist is something that, again, from the outside that gets into the brain. And so this, let's say that this releases ACH, but an antagonist gets in and blocks the ACH receptor site, so the ACH can't get through. Okay, and a neurotransmitter, a good way to look at a neurotransmitter is a key that opens up a lock. So it has to be the right neurotransmitter to fit the right lock. So if we're talking about serotonin, serotonin has a key that if it fits the receptor site, it can open it up and cause this neuron to fire. Well, what an antagonist does is it blocks the lock so the key can't enter. Okay, so if you've ever heard of venom, for example, venom is released by spiders and snakes. And what venom does is venom will paralyze the person who receives it by blocking the receptor site for ACH. Remember that ACH is responsible for movement, right? So if you get bit by a snake and it releases its venom, it can paralyze you. All right. In fact, baby rattlesnakes, for example, are the most dangerous because they don't understand that you're only supposed to release a certain amount of venom, and they release all their venom. And it, in essence, will paralyze someone to the point where their body will shut down. Okay, and they can die. If you ever heard of curare comes from a plant, and Native Americans used to take curare and put it on the end of their arrows, and when they would shoot an animal, the arrow wouldn't kill the animal, but the curare on the end was an antagonist for ACH, and it would paralyze the animal. And obviously, then they could, kill the animal and eat it. Okay. So the final thing about outside factors I want to talk about within lesson 2C here is, I think it's 2C that we're doing, is reuptake. Reuptake, I'll define it first, and I'll go back to the video, or not the video, but the graphic. Reuptake is when a sending neuron releases a neurotransmitter, or neurotransmitters, let's say. A sending neuron releases neurotransmitters, any neurotransmitter that is not picked up by the receiving neuron will get taken back by the sending neuron. Okay, so it's kind of like the sending neuron releases the neurotransmitters, and this is the receiving neuron, and the neurotransmitters are in the synapse, and whichever neurotransmitter doesn't get taken in, this one sucks them back in like a vacuum cleaner. Okay, and that's what we mean by reuptake. So if I go back, neurotransmitter gets released. For whatever reason, it doesn't get taken in. Maybe there's not enough receptor sites, like I said, or whatever. So rather than staying in the synapse and, for lack of a better term, causing, kind of just like a dirty synapse, the sending neuron will suck it back in, okay, and put it in the vesicle for next time. So if you or anyone is on an antidepressant, or sometimes anti-anxiety meds too, are called SSRIs. And SSRIs, in fact, can I do this? I should have capitalized the R and the I. But SSRIs are antidepressants that block the reuptake of serotonin. Okay, so I didn't mention this, but you need to know what an inhibitor is, okay? And if something inhibits something else from happening, it doesn't allow it to happen. It stops it, right? So when we say reuptake inhibitor, it's stopping reuptake. What is it stopping reuptake of? Serotonin. So let's go back to this. So if Prozac, Zoloft, Xanax, a lot of antidepressants are SSRIs. So here's how they work. This sending neuron releases serotonin. What happens with a lot of people with depression is that they don't have enough receptor sites for serotonin. So the serotonin gets released into the synapse, and then reuptake occurs, and it gets sucked back into the sending neuron, right? Well, what SSRIs do is, if let's say that these green things are the vacuum that suck up the neurotransmitters in the synapse, what SSRIs do is they block this gate from opening. So the serotonin goes into the synapse. It doesn't get picked up by this one. So it starts to go back, but it gets blocked and bounces back into the synapse, where it can then get taken by this receptor site. So let's say that this neurotransmitter releases 3 neurotransmitters of serotonin, but there's only one receptor site. So this one takes one of the 3. There's still 2 bouncing in here, right? So they're about to go back, but the SSRI blocks them. They stay in the synapse and it goes in. The third one tries to get in, it can't. So then it gets there. So this receiving neuron without the SSRI would only be able to take 1 neurotransmitter of serotonin, but in this case it gets 3 because the reuptake was prevented, and it allows it to stay in the synapse longer. Okay, so that's how SSRIs work. Okay, other drugs, like any other drug, like heroin, cocaine, any type of drug that makes alcohol that makes you feel good. The problem with those, especially the stronger ones like crystal meth and heroin and drugs like that, is that they mimic, or they are agonists for neurotransmitters that make us feel good. So they get into the synapse and fill the receptor sites, we feel good. But then the problem with that is the brain realizes that these neurotransmitters are coming from an outside source. So they stop producing it, right? So this brain is going to be like, well, I don't need to produce dopamine anymore because you're getting it from a different source. And that's when a person feels bad after the high wears off, and that's where they begin to need more of that drug. Okay, so this follows up the other neuron video, and it specifically refers to neurotransmitters, and these are the ones that we're most concerned with remembering.